So first of all, you did pretty well on the quiz, and well, it's a good thing if you did well. It's not a good thing if you didn't do well, because well, you should have done suggested problems, and probably the next quizzes will be a little bit harder, not much harder. The midterm will be like well, kind of harder than the quizzes, and well, the final will be something in the midterm. So, if you have any questions about the grading of the quiz, just come to me and I will either answer them or just take a quiz back to the TA and she will regrade it. What else? So that's it about the quiz.
What about the average?
The average, I don't remember. It was pretty hard. I mean, something like 7 plus. Okay, so yeah. So last time we talked about so last time we just did some computations, something like 2 less digits of 2 to the power 1001 or something like this. We dealt with raising some number to some large power and decided what the answer is. And what helped us was using Fermat theorem and Euler's theorem. Let me call what they are. So now Euler's theorem is the following statement: if B is prime and C does not divide some number A, then A to the power of B minus 1 is pointing to 1 modulo B. So we use this kind of theorem, and it was very useful if you want to compute a number like 2 to the power 1 million modulo some small prime p, say 7. On the other hand, well, the same statement, when you reformulate it, it's like a different way. If P does not divide A and A to the power of E, let me change P to N, A to the power of N minus 1 is not congruent to 1 modulo N. What's the conclusion? If you have some number A, such as once you raise it to the power N minus 1 and reduce modulo N, you don't get 1. According to Fermat theorem, the only possibility that N is actually not a prime number. Then N is not prime. In other words, for this is compact. It has at least 2 distinct factors, not equal to 1, not equal to N itself. So it's the same statement, it's just formulated in a different way. But once I formulate it this way, it gives me a kind of way to know that some number is not a prime number without actually factoring. What do I mean? Suppose I want to verify, so here's an example. Suppose I'm suspecting that some number, something like 91. So somehow I decided that 91 is suspicious enough, it could be prime. I think so. Actually it isn't. And some of you might know factorization of 91 to prime numbers, but yes. But I don't want the factorization. I'm just saying, well, somebody came to me and told me, well, 91 is suspected to be a prime. And one of the tests is, oh, if I don't want to actually factor, how would I know is it a prime or not a prime? Well, one of the possible tests is do the following. Take a number which is not divisible by 91, say 2. So this will be my A. Take this number 2 and raise it to the power 91 minus 1. Well, that's a large number. It's very interesting, it's very long, hard to compute. But what is much easier is to compute what is this number modulo 91. In particular, the question is this number congruent to 1 modulo 91? If it is not congruent to 1 modulo 91, then I can conclude that 91 is actually composite, cannot be a prime number. If it happens to be congruent to 1, well, this tells me actually nothing. I mean, it could be congruent to 1 because 91 is indeed a prime. It could be congruent to 1 by some random chance or something like this. You'll see examples where this test doesn't work. But in this example, let's actually compute what is 2 to the power 90 modulo 91. So maybe any ideas how to actually compute this number?
Break the exponents apart, and then take succession its power, and then mod 91 multiply together. That gives the manageable part.
Okay, so one idea is like this. 90 is, say, 2 times 45. So let's compute, instead of 2 to the power 90, so the question is how to compute 2 to the power 90 modulo 91. Well, one idea is like this. Let's indeed break this exponent apart. 90 is idea. Well, let me take 2 to the power 90 and rewrite it as 2 to the power twice 45. Now I can write it as 2 squared to the power 45. Well, that's the same as 40 to the power 45. Okay, so if initially in the name way I have to multiply 2 by itself 90 times, now I have simpler task. Multiply 4 by itself 45 times. Yeah.
Why don't you put the 5 function here with the word? If A doesn't like n, then A would be phi n. Is it similar to 1?
Okay, so the problem is, how do I compute phi of 91?
Oh, but then you have to decompose it. So it's
Yes.
the same thing.
So to actually, well, it is a great idea indeed. I mean, we always use this trick. How to compute 2 to some large power modulo some number? We'll take this number, compute phi of this number, and use Euler's theorem. 2 to the, well, a to the power of phi of n is congruent to 1. The problem is, how do I compute phi of 91? One possibility is all the numbers from 0 to 90, which are, well, relatively prime to 91. That's long. I mean, that's the same as actually trying each factor from 1 to 90 and seeing whether it relates 91. That's at least as much work as actually factoring 91 to factors. Another idea is, well, take this 91, write it as product of relatively prime factors, and we'll use the formula instead. Once again, write it as a product of relatively prime things, it means factors. If I do not want to factor it, well, that's what I can do.
And if you could figure out what phi of 91 is, then you already know that it's phi of 91.
Yes, exactly. Exactly. Yes. Okay, so back to here. From here I can continue in several ways. One way is, well, 45 is 3 times 15, so I can compute what is 4 cubed. It turns out to be what, 64, and try to raise 64 to the power 15. And then, well, 15 is 3 times 5, and so on. Well, I wanted to demonstrate slightly different way. I mean, this way actually depends on the fact that 45 is kind of a special number. I want to demonstrate a way which is applicable kind of always. I want to apply this very trick. The 45 is not even. It's odd number. So I can rewrite it like this. 4 times 4 to the power 44. And now apply the same trick to compute this number. Now this is 4 times 16 to the power 22. Once again, it's the same as 4 times 256 to the power 11. Well, starting from here, I already can't multiply that fast. I mean, I really can't square 256 in my head. But what I do instead is reduce this modulo 91. I mean, what I'm actually interested in is not the answer. It's only the answer modulo 91. So instead of computing this, I'll continue this way. 4 times 256 to the power 11 is congruent to 4 times, well, let's reduce 256 modulo 91. It is, what is it? 91 times 3 is 173. Sorry? 74. So 74 is a large number. I'd rather write it as negative, so I have to add, well, to get 273. So 273 is 3 times 91. So I'll have to add negative 617. Well, now it's much simpler to deal with 17 instead of 256. Much less operations to do. Well, let's continue. Once again, I want to apply the same trick. So rewrite this as 4 times negative 17 times negative 17 to the power 10. And now 10 is twice 2 times 5. Oh, here are actually quantities. So it's 4 times negative 17 times 289 to the power 5. Once again, 289 is, well, is a large number, but I'm not interested in the number itself, only in its remainder modulo 91, which is, well, we see from here, it is 16. So it is congruent to 4 times negative 17 times 16 to the power 5. Well, we have a few extra calculations which we can, well, finish pretty fast. So this is 4 times negative 17 times 16 times 256 squared. I'm doing the same trick over and over again. But now I'm actually left with pretty small numbers. 256 modulo 91 we already figured out. It is congruent to 4 times negative 17 times 16 times 256 is another minus 17 squared. Well, it is a long computation, but it is coming to the end. So finally, well, not finally yet, but almost. It's the same as 4 times negative 17 times 16 times, well, minus 17 squared we already computed. It's 289 modulo 91 plus 16. And the last step is just multiply these 4 numbers. Once again, not a big deal. You can multiply them in couples and reduce modulo 91. 4 times minus 17 times 156. So it is 4 times negative 17 times negative 17, which is 4 times 16. We already did the computation many times, which is 64. And finally, I have to add all the computations have been performed to modulo 91. So, well, initially I had to perform kind of 90 multiplication to compute 2 to the power 90. By using this trick, I performed much less. I counted in at home, I performed about 15 computations. Really much less. And of these computations, several were actually kind of the same computation. It was 16 squared or minus 17 squared, modulo 91. So basically I performed, well, if I wanted to compute distinct computations, I computed maybe 7 different products, something like this. So actually this computation, well, it was kind of long, but not very long. And the result of this computation is, well, I know that two to the power 90 is congruent to 64 modulo 91. Hence, 91 is congruent. They just Fermat-Little theorem. If it was a prime, then the answer here would be 1. But it isn't 1. We just computed it by hands. Well, what are the lessons out of this computation? Well, what are not the lessons? The lesson is not that 91 is congruent. Well, it is actually not hard to actually verify by hands. It's something like what? 7 times 13. Yeah, 7 times 13. It's not that 2 to the power 90 is 64 modulo 91. The lesson is that if you want to compute let's formulate the lessons. Lesson number 1 is as follows. If you want to compute a to the power k modulo n, some number k would be very large. Some number a, once again, could be large. Some number n, once again, could be large. How many computations should you perform? Is it k different multiplications? Well, no. You can do it by kind of successive squaring. If you have to compute a to the power twice n, compute instead a squared to the power n. If you have to compute a to odd number, compute instead a times a squared to the power n. Well, so use these tricks. By applying these tricks repeatedly, we can do it, well, we can find the answer. So it will take you, it takes about, well, kind of 2 or 3 times log of n is base, log of k is base 2 multiplications. Of numbers which are at most as large as n's. So once again, why is that? At each step in our kind of algorithm, we are replacing such computation by such computation. Well, at each step we are performing one product or maybe 2 different products. And we are simplifying our problem by a factor of 2. We are decreasing k by a factor of 2. So how many times do we have to decrease this k by a factor of 2 until we get something manageable? Well, basically, log of k is base 2. We just find some power of 2 which is larger than k. And then at each step we are introducing, well, 1 or 2 multiplications, so maybe this concept is better described as 2. So instead of performing k multiplications, we can perform just log of k multiplications. Log of k is, so if we are performing operations with, say, numbers with 100 digits, this number will be something like 300. Log of such number modulo 2, where it is base 2. So it's really kind of fast. The computer can perform it really fast. On the other hand, doing it in the direct method by just performing number of multiplication, which is, well, which has only 100 digits in, well, if you write this number, it has 100 digits, well, that's something which is not manageable even by computer. So this method is actually, well, you can take a huge number, a number with 100 digits, and test whether it is composite using this method. So the second lesson is using this method in computing a to the power n minus 1 modulo n. You can sometimes, if you are lucky enough, prove that n is composite. So if this number, the result of this computation, is not equal to 1, then n is composite. If it happens to be 1, well, we can't conclude anything. It could be the case that n is prime, it could be the case that, well, we just weren't lucky enough. We didn't choose good enough A maybe. Or maybe just the problem is too complicated. Maybe it happens that for all possible A's, we actually do get 1. Let me show you an example. Maybe before an example, any questions about this? So maybe once again, if I want to formulate the lesson in the shortest possible way, what you should actually remember is as follows. Solving this problem, raising some number to some power modulo a given number, is computationally cheap. You can actually do it, well, either by hand or using a small computer. So let me give you kind of example exercise, a non-example. Non-example. If I take n to be 561, this number, well, I'll tell you what it is. First of all, it's divisible by 3. That's easy to see. If you did your homework, you should know that the number is divisible by 3 if and only if some of its digits is divisible by 3. Here it is 6 is divisible by 3, and 5 plus 1 is also divisible by 3. So this is divisible by 3. Next, it is divisible by 11 and by 17. So I'm going to take this number. So my claim is as follows. For any A which isn't divisible by by 11 or 17. So any number A which is relatively prime to n. So we say that GCD of A and n is equal to 1. Turns out that in this example, actually compute a to the power n minus 1 modulo n, we always get 1. So if you take, well, in other words, a to the power of 560 is congruent to 1 modulo 561 for a such that GCD of a and this number is equal to 1. So for this particular number, our kind of completeness test, well, it will work sometimes. I mean, if I happen to choose a to be one of the factors, then yes, I won't get 1 as the answer. But, well, if I am lucky enough to just guess the factor, then I don't need any further steps. But if I'm not lucky enough, if I choose a to be 2 or I choose a to be 5, whatever, and I raise it to power 560, I will get 1. Let me show you why it is true. Maybe somebody already solved this problem. Okay, so Euler's theory. So one idea is, how do we show that a to some power is congruent to 1 modulo a number, modulo, and, well, one of the things we know is Euler's theory. So it tells us that if GCD of a and 561 is equal to 1, then a to the power of 500, a to the power of 561 is congruent to 1 modulo 561. What is 561? Well, let's compute. 5 of 561 is, we have factorization, 3 times 11 times 17, is 2 times 10 times 16. So it is 20 times 16, 320. Well, not really that much help. I mean, what I wanted to show, so I know that a to the power 320 is congruent to 1 modulo 561. And what I want to show is that a to the power 560 is congruent to 1. So I really don't see how to go from here to there. So Euler's theorem is just not enough. I mean, it is useful. It shows that instead of showing this statement, I can instead show that 5 to the power of a to the power of difference is congruent to 1. But still, it's not strong enough. So the other idea is, well, I want to know what is this number modulo this number, 561. Modulo this product, 3 times 11 times 17. Which is remainder theorem. It is the same as knowing, as learning what are the remainders separate, modulo 3, modulo 11, and modulo 17. If you know the remainders separate in modulo relatively prime numbers, you can combine this information and get the answer, the remainder modulo of the product. So let's try doing this. So another idea, maybe here I should say, this is not enough. So another idea is like this. Let's compute a to the power 560, but not modulo the product. Let's compute it modulo 3, modulo 7, modulo 11, modulo 17. Well, that's much easier. Why is it easier? Here, I can write a to the power 560 as a squared to the power 280. Does anyone see now why this is equal to 1 modulo 3?
A square can.
Okay, so one explanation is, yes, a is relatively prime to 3, so modulo 3 could be 1 or negative 1, let's say. I mean, all the remainders modulo 3 are plus 1, negative 1, and 0. It's not 0 because a is not divisible by 3, so it is 1 or minus 1. Both 1 and minus 1 squared are 1s, and raised to the power 280, 1 to a power is congruent to 1. Okay. A to the power 560 is, let me write it like this, a to the power 10 to the power 56. Why is this number congruent to 1 modulo 11? Yes. Yes, exactly. So Fermat-Little theorem applies here. 11 is prime number, and a to the power 10 by Fermat-Little theorem is congruent to 1. So this is the same as 1 to the power 56, which is 1 modulo 11. And here I used Fermat-Little theorem. And finally, I want to conclude that it is also 1 modulo 17. Or rather, compute what it is modulo 17. Well, once again, by Fermat-Little theorem, I know that a to the power 16 is congruent to 1. So let's divide this by 16 with remainder. What is it? Yes. So 560 is 8 times 70 or 16 times 35. And this is, once again, congruent to 1. Same reason, Fermat-Little theorem. Okay. And finally, the argument is as follows. I have the same number, a to the power 560, and I know what are the remainders of this number, modulo 3, modulo 11, and modulo 17. I want to reconstruct what is the remainder modulo of the product. Chinese remainder theorem tells me there is only one way to reconstruct it. And the question is, what is this way? So Chinese remainder theorem tells you there is only one number between 0 and the product of 3 times 11 times 17, such that this number, modulo 3 is equal to 1, modulo 11 is equal to 1, modulo 17 is equal to 1. We know such a number. 1. Yes, of course. Just take 1. So by Chinese remainder theorem, a to the power 560 is congruent to 1 modulo the product. We explain once again what the argument was. Chinese Chinese remainder theorem tells you that there is exactly one number x between 0 and 3 times 11 times 17, which solves this called system of congruences with x congruent to 1 modulo 3, x congruent to 1 modulo 11, and x congruent to 1 modulo 17. And x equal to 1 is such a number. In this particular case, there is a simpler argument. Just a to the power 560 minus 1 is divisible by 3, by 11, and by 17. Hence, this number minus 1 is divisible by the product. But, well, you should get used to applying simple general statements like this, or getting used to simple kind of arguments like this. I mean, you should know even before you get to this point, the Chinese remainder theorem, whatever answers you get here, will let you know what will be the answer modulo the product, without actually figuring out what it is. You should know that at least it will, for sure, it will give you some answer. Okay, so we prove this statement. So for this particular number, 561, our kind of test for being composite will fail most of the times. I mean, if you choose this state randomly, basically any number which is not divisible by 3, 11, or 17, our compositeness test will tell nothing, just nothing. So it is a good test sometimes. Well, it is good precisely when it works. And it does frequently work. But for some numbers, it just doesn't. Okay, so maybe any questions about this? Okay. Maybe I'll just formulate the kind of problem and we'll start solving it after the break. So the next thing we are going to discuss is the problem how to solve equations of the kind of the form x to some power k is congruent to b modulo m for given k, and n. So you're given such an equation, k, b, and n are some given numbers, and you want to find all possible x's modulo this number n, which solve this equation. So basically, instead of raising to just usual power, b to some power k, what you want to do is raise to fractional power, extract the case root of b. It turns out that sometimes actually you can do this, and you can do this effectively. Meaning, well, I will give you a break which is suitable for actual computations. So let me formulate what we are going to do, and then we'll have a break. So we will see. This problem can be solved kind of quickly. If BCD of k and n and 5n is equal to 1, so n5 is known. Okay, so let's have a break and then we'll discuss how to actually solve this question.